Here's a system of linear equations, 3 equations, 4 unknowns. It perfectly fits into this general, this long, big structure I put on the projector in the very first moment of today's lecture. You see, I even wrote it in a way that the identical unknowns, they're just sitting one above the other. So you can even in this system, in this form, you can recognize the augmented matrix. So now I'm going to follow the Gaussian elimination method exactly the way I described it on my slide before the last one. So first I extract my augmented matrix. Here it is, coefficients 1, 2, 4, first column, 1, 3, 2, second column, 0, negative 1, 2, negative 1, negative 1, 1. Right hand side, negative 3, negative 15, negative 1. So here it is. Here's the extraction. First row, from the first equation, you see the missing coefficient went into 0. Second row, from the second equation, 15. Last one. And here's my augmented matrix. Normally when you make the steps in your Gaussian elimination method, you connect your stages with arrows. And see my arrow is already here. So the principal steps when you work in your Gaussian elimination is you have to vanish as much as you can under these pivots, right? So when I look at this system, I see that this will be my first pivot when I'm finished with this, and I'm going to use this pivot to vanish everything under that pivot. This 2 and 4. The row reduction operations which are required, they are like this. I have to multiply the first row by negative 2 and add it to the second one. And I also have to multiply my first one by negative 4 and add it to the third one. These two operations, this time I will do them in one. Actually, that last time I also did it in one go. If I do these operations, that will vanish these two elements under my chosen pivot. Here's the result of this. First row is totally unchanged. Second row, 0 as predicted. Here will be negative 2 and 3 is 1. 0 and negative 1, negative 1. Negative 2, it's 2 plus negative 1 is 1. And here will be negative plus 6, plus 6 and negative 15, it's negative 9. The result of this operation on the last row, 0 as predicted. This element is negative 4 and 2 is negative 2. This is simply 2 because we have a 0 here. Negative 4 and negative 1, it's 4, and 1, it's 5. And 11 here because we have 12, take 1 is 11. So now I have two pivots. One of them, is my first pivot. Is the second candidate for the pivot. I can use this pivot now to do my final step of the Gaussian elimination method, reading of this negative 2 or converting this negative 2 to 0. And the row reduction step required for that is this one. I use my second row, multiply it with 2 and add it to the third one. If I do that, here's the final step of my Gaussian elimination. First row is totally copied. Second row is completely copied. And the last one, that's where the changes will happen. 0 as predicted here. We have plus 2, right? So it's a 0 here as well. And we have here 2 plus 5 is 7. Right hand side is negative 18 plus 11. It should be negative 7. Yes, it is. If I take these two pivots, if I duplicate that, here's my pivots here. Surprise, surprise, it doesn't fit. Here's two pivots here, and here's another pivot here. If you now remember the criteria for the row echelon form, they all fully met here. All 0 rows at the bottom. We don't have any 0 rows, and that's good. and every pivot in a row is further to the right than the pivot above it. If I remember now that, look at this. This was the column which is the unknown x1. This is the column which is unknown x. Now I do the back. I'm preparing my back substitution now. So I'm going to convert my matrix back to the system. Here's a column which corresponds to the x3, column x4. It's the right hand side. Yes. Now the extra information which we can learn from this system is this. You see, that's the first example. Well, we had two examples today. That's the first example which you see today, where not every column on the left-hand side is the leading column. Remember, the term leading column means the column which carries a pivot. Here's a column which doesn't carry any pivot. With such a column, you see, I hope you're convinced by now that if you have a perfect triangular shape on the left-hand side, meaning that if you have all columns on the left-hand side leading ones, you can always back substitute, right? Something we did with you on the first example, something was quite obvious on my second example. I didn't do that, but it was there, right? Look at this, what happens here. Here we have three columns with pivots, three leading ones, and one of them, which normally called non-leading column because it doesn't have any pivot. Think about this trick. If I do the conversion back to the system of linear equations now, if I put my unknowns back in, remember I just said this, when you have a perfect triangular shape, all leading columns on the left, you can always back substitute. Now look what I'm going to do now, how I'm going to handle the column with no pivot. Look what I'm going to do. I'm going to write, I'm sorry, I'm going to convert my back to the system, but the unknown, this unknown next to this non-leading column, I'm no longer going to write this on the left-hand side because I don't need it there. I need perfect triangular shape on the left-hand side to back substitute. This column will be a problem. I mean, it will be standing in the way of a perfect triangular shape. I'm going to get rid of it by just tossing it on the right-hand side. Well, and normally when people do that, they also do the other thing, which they call parameterization, because these unknowns, which correspond to the non-leading columns, we don't need them on the left. Just to keep this in mind. Back substitution need the perfect triangular shape on the left-hand side. So this column, we just put it there, and we still can solve for the rest of the variables. It's a back substitution thing. I'm going to move it on the right-hand side, but the unknown is no longer, we're going to use the term x3 for that. We're going to use a more suitable, well, x3 should be perfectly good, but normally, conventionally, people just use a parameter like lambda, for instance, for that variable. And if I do that, look what's going to happen. Here's the line I will come up with if I use the first row of my row echelon form, x1, x2, no lambda, nothing to go to the right-hand side, negative x4, and negative 3 on the right-hand side. Here's a line which appears basing on the second row. Nothing for the x1, 1 for x2. This one will go to the right-hand side, 1 for x4. Here's my right-hand side. Here's my x3. Just I renamed it into lambda. And the line which corresponds to the last row is 7x4, negative 7. You see, perfect triangular shape here. The one which can be easily back substituted. The only difference this time will be is that when I do back substitution, my result, my solution, it will carry this lambda there. What does it mean? It means that no matter which value I set for lambda, the triple of the rest of the numbers, the triple of x1, x2, x4, it will always be a solution. No matter what I set for lambda, the rest will always be a solution. For x3, I'll take the value I set for lambda. It means that we have multiple solutions, infinitely many of them. For every chosen lambda, I will come up with a solution. So if I back substitute, I think I back substituted somewhere here. Let me just lift it a little bit. Here's my back substitution. x4 is negative 1, right from here. x2 or x3 is lambda. That's my setting here. I just set it like this. x2, look at this. If I back substitute here -1 is the x2 result. It carries lambda as promised. And back substitution for x1, here it is. Here's my complete solution. Look at this. I take any value for lambda, and that will give me a solution. Take lambda 0, it will be 4 numbers, which will be a solution. Take lambda 1, it will be 4 numbers, which give me the solution. Take lambda 2, 3, any other number, including complex numbers, by the way, even though we don't look into that in this topic. That will be a solution. And so the general thing which we can come up from here is that when you end up with the row echelon form on the left-hand side with non-leading columns, you can always do this trick. You can always parameterize the unknowns corresponding to the non-leading columns. You can always come up with the multiple solutions. Almost always, I guess. I hope even at this stage you realize what's the benefit of the Gaussian elimination. You see, without that, you won't. It's a very strong claim with which we made right now. By looking at the augmented matrix or row echelon form of the augmented matrix, we can just predict how many solutions will system have. Will my system have? Yes. You can't do this with the ad hoc solution. You can find maybe a solution quicker, but making this general prediction, it's already advantage. That's the reason. That's one of the reasons, very first one, why we study Gaussian elimination method. Now, when you look into this, when you look at this system, sorry, do you recognize anything? Anything familiar? I mean, sorry. When you look at this solution, do you recognize anything familiar? If you treat your x1, x2, and x3 as components of four-dimensional vector, if you treat your x1 and x2 as components of four-dimensional vector, you can write this right-hand side, you see, this right-hand side, in this form. Here's the numbers from the right-hand side with no lambda, 4, -8, 0, -1. Here's the numbers which are next to lambda on the right-hand side, -1, 1, 1, and 0. When I write this in this particular form, you can recognize here the parametric form of the line in four-dimensional space. So not only we concluded we have multiple solutions, we also concluded that the solutions, in fact, they form a line in four-dimensional space. You see how many interesting things we could come up with if we just do this Gaussian elimination method. And actually, that's the main advantage of the this broader scope which I promised to you. You can think of a solution not just individual points you're looking for, but as a geometrical entities.